Good afternoon, students. Welcome back once again to the mathematics class. So, in the last class, we have completed our last exercise, that is integrals. This is last exercise, that is 7.11. Now, we are moving towards our next chapter. It is nothing but application of integrals, right? So, what are the applications of integrals are over there? So, let's see in this chapter. So, here already we have learned elementary geometry were used to calculate the area of many simple curves we have seen, like triangles, rectangles, trapezia, and circles, etc. Already we know how to calculate the area of these curves, right? So, but these are inadequate for calculating the areas, so which are enclosed by the curves. So, here we shall need to some concept of integral calculus. It is nothing but what we are going to study, that is nothing but application of integral. So in the previous chapter, that is integrals, we studied to find the area bounded by the curve, that is y equals to the curve in general what we have taken, y equals to f of x, find the ordinates x equals to a and y equals to b, and the x-axis by calculating the definite integrals as limit of a sum we have studied in the previous chapter, in the integrals chapter, right? So now we shall study the specific application of integrals in order to calculate the area under the curve. Area under the curve, right? Or area between the line and arc of a circle. Area between the line and arc of circle. Parabola, ellipse, and also we shall find the area bounded by above mentioned curve. Above mentioned curves, right? So before going to start application of integrals, we have to know how to draw the graph. First of all, we have a basic idea about the graphs, how to draw graphs and which kind of a graph we are going to write and how it should be. We are aware of that basically. Later on we can find the area or the region of the curve. Area under the curve or bounded region also we can find easily. So let's see first some basic types of graphs. Already you are familiar with this in your 11th standard, you have studied in a conic section. So generally the circles x square plus y square equals to a square, right? So what we have, the graph is like this, right? So it is a point O, the point P of x comma y, right? It's a x-axis, it's a y-axis. So it's a equation of circle when whose center is origin, that is whose center is what, origin, 0 comma 0, it's a center, and the radius is a here, right? So next, one more graph we have, that is For this equation, x minus h whole square plus y minus k whole square equals to r square. It is central form, we can say. So here also we have a circle. The center point is C, h comma k. It's a r, so it's a point P, x comma y, right? So next one more we have x minus x1, that is diameter form, we can say here. That is x minus x1, x minus x2 plus y minus y1, y minus y2 equals to 0. So it is a diameter form. So let's see, it's a diameter form. So it's a point P of x comma y. It's a x1 y1, b x2 y2, right? So these are the types of graphs we have in a circle. So next we have the parabolas. How the parabola graph, let's see. So in general, the parabola graphs are like this. So when y square equals to 4ax, y square equals to 4ax, let's see, y square equals to 4x, the graph is like this, right? Again it is x-axis, it's a y-axis, somewhere where it's a length of lattice rectum, the reason we have to find like this, right? So it's when y square equals to 4ax, and similarly when y square equals to minus 4ax. In that case, what we have? So it's our parabola. The reason is like this. We have to find here x-axis, it is y-axis, it is negative x dash, it's negative y dash, it is origin. So when x square equals to 4ay, in this case we have the graph like this. See, the graph is, let's say, length of lattice rectum. The reason what we are going to find here, it's ellipse when x square equals to 4ay. Already you are familiar with this also. And next one more, finally x square equals to minus 4ay. It's below the x-axis, right? So like this. The curve is like this. Right? So the reason we have to find like this. X-axis, it's y-axis, it's negative y-axis, it's negative x-axis, right? So these are the graphs of parabola. So next we will see the graphs of ellipse. So just I am giving introduction how the graph should be and how we plot a graph. So next, ellipse. So here we have ellipse formula is x square plus y square by b square, which is equals to 1. In this case, what we have, so the graph is like this, right? So it is x-axis, it is y-axis. So two foci we have here, f1 and f2. It's a point P, x comma y, right? So we have to find the region like this. The four region if we have to find means we have to all the four parts of the ellipse when it is x square by a square plus y square by b square. So next we will see the hyperbola. So the graph of a hyperbola is x square by a square minus y square by b square. X square by a square minus y square by b square, which is equals to 1. So the graph like this, what we have here, let's see. So it is nothing but our length of lattice rectum L and L dash. So the reason what we are going to find here, this reason, right? So it's a focus F1 here, it's a focus F2 here. Got it? So these are the what? Graphs of different types of curves. It is circle, hyperbola, ellipse, and finally parabola, right? So now we will see how to find area under a simple curve, right? So up to now we have discussed about the graphs only. So now we are coming to the main portion of this concept. Area under simple curve first, right? Area under simple curve. So already you know, if we have it's a x-axis, it's a y-axis, right? Let's see, we have a curve like this, a curve is there like this. So to find here what we have, so let's say write in detail. For this, let's considering the first one, A. To find area bounded by the curve y equals to f of x, x-axis, and the ordinates x equals to a and x equals to b. So here we have the curve. See, it is y equals to f of x. The curve usually you have to take it as y equals to f of x, the curve. So here the ordinates we have a and b are the two ordinates. A and b are the two ordinates. They are perpendicular to x-axis, right? These two are perpendicular to x-axis. So it is aligned and we are taking these points. So the strip what we are taking here, so it is a strip we are taking here. This strip is nothing but what we can take, it's a dx, and this strip is nothing but y, which is parallel to y-axis. So we can say it is x equals to a and it is x equals to b, right? So now let's see here the required area. The required area is composed of is composed number of thin strips. What we are taken here, strips, it's important here. Strips, let the arbitrary strip be of height y. See, we have taken in the graph. See, it is nothing but y, height is y, and width is dx. And width dx. See, it's a width of the strip dx. Then dA, area of elementary strip. Area of elementary strip, which is nothing but y equals to dx, where y equals to what? Y equals to f of x. So what we are finding here, the area under the simple curve. So it is nothing but our curve. It is our curve, right? What we have, it is our curve under the region. See, what we have, this region, this much region. You have to find area of this region. It is under the curve. What we have, the region we are finding by using the strips. What we have written here, thin strips, composed number of thin strips. So by using thin strips, we are finding the area under the curve, whereas its height we are taking as y and its width we are taking as dx. Then the area dA is nothing but elementary strip y equals to dx. So this area is known as was elementary area. This area is known as, this area is known as elementary area, right? So a total area of a region, so total area of the region ALMB, which is equals to integration of x equals to a to b, that is limit function dA. So hence what we have, a equals to integration x equals to a to b y dx, whereas integration a to b y is nothing but y equals to f of x dx when it is with x-axis. The curve is with x-axis. So next, see, in the graph we have, so it is according to x-axis, right? So it is on x-axis, we have seen here. It's with x-axis. So when the curve is it y-axis, so when the strip what we have to take it to the curve is parallel to what, x-axis. When the curve is parallel to y-axis, in that case how we have to find the area under the curve, let's see. So next B, second one, to find the area bounded by the curve x equals to g of y, right? So in the earlier case we have taken y equals to f of x, but now in this case we are taking x equals to g of y with y-axis, that is y-axis, and the line and the lines y equals to c and y equals to d. So let's see. See, the curve is like this now, right? So what we have here, it is point A, it's point B we have taken. So next we have to connect this. So here the strip, we are taking the strip. The strip is nothing but it is dy, and this strip is horizontal, taking x. So it is y equals to c, it is y equals to d. Got it? So it is the curve x equals to g of y. X equals to g of y. In the previous case, what we have? The strip is vertical. So here the strip is horizontal, right? So let's see. The required area is composed. The required area is composed of a number of thin horizontal strips. Thin horizontal strips. So let arbitrary strip be a length x and width dy. So then dA equals to area of elementary strip, which is equals to x dy, where x equals to g of y, right? So let's see the area what we can find here. A equals to integration y equals to c to d x dy. So let's see here what we are in x dy, which is equals to integration c to d g of y with respect to dy. So by using in this reason, we have to find the reason like this. By taking the strip, we have to find the reason like this. The area under the curve. So here the curve is what? The curve is x equals to g of y, right? So we are finding the area under the curve. So similarly, we'll take one more. Sorry. So let's see. In remark, we will see when the curve under consideration is below x-axis. When the curve under consideration is below x-axis. Is below x-axis. So let's see the graph. So the curve is like this. So here what we have, it is origin. So x-axis, it's a y-axis. So this is a curve y equals to f of x. So here the points. So we have this much area we have to find here. So it is x equals to b. Is x equals to a. We have considered the strip here, right? So now in this case, so this reason we have to find here, right? So let's see here, f of x is what? Less than 0 here, right? The function f of x is below the origin of x-axis, right? So x-axis is less than 0 from x is a to x equals to b. So therefore the area bounded by the curve x-axis and ordinate x equals to a and x equals to b will be negative, right? So you can consider the number of value in this case. So we consider number of values in this case. The required area is mod, we are taking mod integration a to b f of x dx, taking absolute value here, right? So the values are what here? Negative. So we are taking mod for that. So required area is mod integration a to b f of x dx. So next, second case, when the curve under consideration, when the curve under consideration lies above as well as below x-axis. When we have both the cases, the curve is above x-axis as well as below x-axis. In this case, how we can take, let's see. See, we have a graph. See, the curve is like this. Right? So here we have to find the reason like this. So we are taking strip here. Here also we are taking strip. This reason we have to find here. X-axis origin, y-axis. So we are taking it as A1, this as A2. So it is x equals to b. Here it is x equals to a. So let's see here how we can take the values here. Here a1 is less than 0, right? It is below the origin. And a2 is greater than 0. It's above the origin, right? X-axis. So then a area of the region is given by A equals to mod A1 plus of A2, right? Mod A1 plus of A2. A1 in the sense the reason what we are taking here. Say in general, the reason is nothing but it is mod integration A to B f of x dx. Similarly, integration plus of A to B f of x dx. So in general, we are taking the values sum of these two terms. So here we are taking mod to the first term because it is the negative of a x-axis. Below the origin we are taking below value. So it's a negative x-axis. So we are considering that as positive value by using absolute value, that is mod value, when the curve under consideration lies above as well as below x-axis. In this case we have taken the solution of this graph like this. It is A equals to area, it is mod A1 plus of A2. So next we will see one or two examples what we have in our NCRT. Let's see first example. So next the area let's see. Next we will see this point, later on we will see examples. Area of the region bounded by a curve and a line. Bounded by the curve and a line. So here we shall find the area of a region bounded by a line and see. In the previous section we have discussed area under the curve only. So now here the area of a region bounded by the curve and a line, specifically a line is adding here, right? So in that case how we can do, let's see. Here it's quite easy, similar to this previous concept. So here we shall find the area of the region bounded by line and circle or parabola or an ellipse. The equation of circle, parabola and ellipse will be in their standard form only. Standard form. So the other forms of the curve are beyond the scope, we can say, beyond the scope of the text. So usually what we get here, a standard forms only we get circle, ellipse, parabola and hyperbola, these cases, and with a line you will get here. For example, I'll show you area of a region bounded by the curve. So let's see, suppose if we have the curve y equals to x square. Y equals to x square if we have a curve. So how will the graph? So let's see, it's the graph for the curve y equals to x square. So now here you have a line y equals to 4, right? So at y equals to 4 you have a line like this. It is y equals to 4 line, and it is the curve x square which is equals to y. So again we have to take strip here. In this case we are taking a strip here. So the strip is nothing but what? It is x. The width of a strip is dx. So you have to find the region of this area, right? So here this is point A, it is point B, so it's the origin, x-axis, it's the y-axis. So with the standard form, either it may be circle, ellipse, parabola or hyperbola. With that you will get a line. For example, what what I have said here, y equals to 4 is a line you are getting here. So with this you will find the area of a region bounded by the curve y equals to x square and the line y equals to 4. So let's see examples one by one. First we'll see the area under the curve. Area under the curve. So the first example of your NCRT solved example is there. The next class purely will solve the exercise 8.1. So now we will take the examples here. First example. Find area enclosed by the circle x square plus y square equals to a square. So let's see here. X square plus y square equals to a square given. So first we have to plot the graph. And on solution. So here the given circle is x square plus y square equals to a square. Take it as equation 1. So this is a circle. Already you know this is a circle whose center is origin, right? 0, 0, and radius is what? Is a. So now plot the graph. Right? So your point x-axis, it's a y-axis, it's a origin. So what we are taking here, we are finding the region of the circle. So if you find there are totally 4 regions here, 1, 2, 3, 4. So if you find any one region, then multiply by 4, then you will get the region of the circle, enclosed region, bounded region of a circle, right? So here we have to find this region by taking a strip. It is y and it is dx, right? So by using the strip we have to find the region of this area. So here, which is x equals to 0, it's a b 0 comma a it is point a comma 0, that is x is a. So now let's see here, the area of a circle, which is equals to 4 times of area of a triangle, area of a region, right? Not triangle, area of a region OABO, right? Bounded by the curve, x-axis, and ordinate x equals to 0, x equals to a. Ordinates are here x equals to 0 and x equals to a, because circle is symmetrical about both the axes, right? So now which is equals to what we get, 4 times of integration 0 to a y dx, taking vertical strip here, taking vertical strip, right? For vertical strip we have with respect to dx. So now just substitute the value here, 4 as it is, 0 to a, that is under root of a square minus x square, because from equation 1 what we have, y equals to under root of a square minus x square. So we have converted in terms of x the given function, the curve, but the reason, but the reason OABO lies in first quadrant, because y is positive. So for that reason we have taken plus under root of a square minus x square. So 4 as it is, integration of under root of a square x square already we have, it is standard form, x by 2 under root of a square minus x square plus a square by 2 sine inverse x by a, limit 0 to a. So 4 as it is, applying upper limit here, a means a by 2, this term becomes 0, plus a square by 2 sine inverse of 1 minus 0 plus of 0. So which is equals to what we get here, which is equals to 4 times of a square by 2 sine inverse 1 is pi by 2. So here 4 get cancelled, it is 4 pi a square by 4 get cancelled, finally what we get, pi a square units is nothing but the area enclosed within the circle, right? So now we'll see one more example with respect to area of a region bounded by the curve and a line. Let's see. See here, first example for this, area of horizon bounded by the curve and line. Next example, find area of the region bounded by the curve y equals to x square and the line y equals to 4. So let's see solution for this one. Standard form, the curve we have with the line y equals to 4. So again we have to find the region, bounded region of the curve with the line. So let's see. The given curve is y equals to x square, take it as 1, and the given line y equals to 4, take it as equation 2. Therefore equation 1 is an upward parabola. If you know the graph of a parabola, then only we can say it's an upward parabola. So initially we have discussed the standard forms of all the conic sections. So here we can say directly equation 1 is upward parabola which is symmetrical about y-axis, which is symmetrical about y-axis only, right? So let's see the graph for this one. So it's a x-axis, it's a origin, it's a y-axis. So what we have here, the line it is 1, 2, 3, it's 4. The point 4 we have a line, it is y equals to 4. So here we have to take strip, horizontal strip. If you find one-sided region, then again we'll get multiply by 2, we get other side also. So it is x, so it is what? It is dy. So what we are taking its origin, it is O, L, it is A, and this is B. So the reason this region we are finding here. Right? So let's see the required area which is equals to area of the region OBAO, which is equals to 2 times of 0 to 4 x dy. Taking horizontal strip right here with respect to dy, taking horizontal strip. So here parabola is symmetrical about y-axis. Symmetrical about what? Y-axis. So we can write which is equals to integration 0 to 4 root y dy. So already it is given from equation 1. From equation 1 we have x equals to root y, because x lies in first quadrant, because x lies in first quadrant. So which is equals to integration 2 as it is integration of root pi is y to the power of 3 by 2 upon 3 by 2 0 to 4. So simply what we can write, 3 by 2 numerator and goes to numerator, it becomes 4 by 3. Now apply the limit 4 to the power of 3 by 2 minus of 0. So 4 by 3 as it is, 4 to the power of 3 by 2 can be written as 8. 8 is cube root, so which is equal to 8 fours are 32 by 3 square units. So note, we can say here a note, the above example can also be calculated by taking vertical strip also, right? By using vertical strip also we can find the above example, that is y equals to x square. So already we have discussed in this lecture area under the curve and area of a region bounded by the curve and the line, right? So in the next lecture we will discuss specifically the examples of exercise 8.1. So from today's lecture the conclusion is what? Application of integrals to find the region of any curve, the region below region, what we have by using vertical strip or horizontal strip. By using the strips we can find the area of the curve under the curve, area of the curve. So it is nothing but, the curve is nothing but y equals to f of x. So integrating we are integrating this curve, this much curve, to find the area of the curve. This area what we are finding by using integration. Application of integration is nothing but to find the area of the curve, right? So that is nothing but application of integrals. So in the next class we will see exercise 8.1. Later on angle between two curves is there, and then exercise, that is 8.2, we will see in the next further class. So till then, take care, stay at home, stay safe.